Recording in progress.
Okay. Welcome again to our seminar series. Today's speaker last week is from the house, is Tony Peralta. Tony actually did his PhD here with Raul, I think, in 2019. Then spent a few years in Vienna as a postdoc, and then he recently rejoined the FISC as a assistant professor. And today he's going to talk about stochastic dynamics of networks, insight into opinion polarization. Tony, the floor is yours. Thank you so much.
Thank you, Sandro. So welcome, everyone. So today I'm going to talk about the stochastic dynamics of networks and polarization. So this is a little bit overview of the talk. So first I divided it in two parts. First, I will talk about dynamics on networks, and then also related to this, I will talk about polarization in online social networks, which would be a real case, a real network that we analyzed. So in the first part, I will talk about what can we do, what are the methods that we have to study dynamics on networks, which can be summarized in individual and complementary approaches, and what are the limitations. So what are the limitations of these approaches, and when do these approaches fail? And basically, they fail in two scenarios, because we neglect dynamical correlations. I will explain later what this means. And also, they fail because they neglect structural correlations. So these are the two main reasons why they fail. And examples where correlations are important are when we have community structure or in other network structures such as spatial or large worlds. And in the second part, I will focus more on a real network related to Twitter and what are the methods to study opinions and polarization in social networks. And for this, we will use embedding and methods and groups, segregation, and stochastic block models. So let's start with dynamics on networks. So, well, when we talk about dynamics on networks, the simplest scenario is binary state dynamics. In binary state dynamics, what we consider is a simple network where we have a set of nodes, and each node has a binary state. Like, for example, healthy, infected, left or right. And this network has some rules, some stochastic rules, where the dynamics, the states of the nodes change in time following some stochastic rules. So this will be a little bit a picture of the problem. Now we have a network with some initial state, and it evolves following some probabilistic rules. What rules? Well, the simplest cases are, for example, we take here a central node that has 5 neighbors, and 3 of them are in the opposite state. They are infected or 1, let's say, and this one is 0. So this central node can change with some rates that we call, because of the epidemic terminology, infection and recovery rates, and depend on the degree and on the number of infected nodes. So this is the big picture of the problem. We have some transition rates, and we have a general network, and we want to study the dynamics. Typical models that are studied, one of the most studied ones are SIS, for example, and the noisy voter. The SIS is one of the simplest infection models. We have each infected node can transmit the disease with some rate, lambda, and nodes recover with some rate that here is the time scale. In this case, the transition rates will be lambda times the number of infected neighbors, and the recovery will be just 1. This is the SIS model, and that is used for epidemic spreading and all other contexts. And another of the most studied and simplest cases, simple models, are the noisy voter model, in which we consider imitation, where the central node imitates the state of a randomly selected neighbor. So for example, we select this neighbor and it adopts this state. And also we have noisy changes where we can have transitions between 0 and 1 just at random. In this case, the transition rates are a linear combination of the fraction of infected nodes and noise. So this is now, in general, what can we do? How can we approach this problem? There are two big types of approaches. One is the individual base, and another one is the complemental approach. What are the differences between these two approaches? The first one that we call individual-based approach is basically we consider the state of each and every one of the nodes. So we have a variable and I for each node, and this variable can be 0 or 1. So we have n state variables, 1 per node. And the network comes in the adjacency matrix. So we consider the full structure of the adjacency matrix. What are the pros and cons of this approach? First, the pro is that of this approach is that it takes into account the full adjacency matrix. We take into account the full structure of the network. But the con is that we cannot use system size expansion techniques. So basically, it's very difficult to obtain a close description of the system. We will come to this later. So individual-based approach, we take into account the full states of the nodes. And for the complemental approach, what we do is we take compartments. We segregate the population in different compartments. And these compartments are the number of nodes in each state. So we make a differentiation between states, the degree, and Q, which is the number of neighbors in state 1. So we take this, the number of nodes which are in state n with degree k and with Q neighbors in state 1. This is the complemental approach. And not all these variables are independent because the sum over n and q has to be fixed by the degree distribution. What type of approximations are typically fit in these complemental approaches are the heterogeneous mean field, which is highly used in epidemic spreading, for example, the pair approximation, and the approximate master equation. But all these approximations are a complemental approach. What are the differences? The differences are in the number of variables. We can restrict the number of variables and simplify these equations, but the accuracy is also affected. What are the pros of this method? In this case, we can use system size expansion techniques, so we can close the system in the thermodynamic limit. Why? Because the variables are a number of nodes, and they scale with system size. So this is one of the advantages of these methods. And the cons are that we only consider the degree distribution of the network, right? So we are neglecting everything that is not in the degree distribution. So these are the two main approaches, but okay, how do we proceed? So we write evolution equations for the variables. The average value, we write the time evolution of the average value is a function of all the variables and is the average of this function. And this is for individual based and also for complemental. We take time evolution of the description variables. The average is an average over a function of the description variables. So we write this equation, these evolution equations, and these equations are not closed, right? Why? Because the average are outside of the argument, So in order to close these equations, what we typically do is just neglect correlations. So instead of taking the average of the function, we take the function of the average. And this is an approximation that is not, in this case, is not controlled, because we don't know what are we doing here, what are we neglecting here. So we are making this approximation. And for complemental approaches, this is valid, but only in the limit of n going to infinity. And by closing this equation, we get a system of differential equation that we can study using fixed points, stability, etc. If the function is linear, this is exact, right? No, but usually, for example, in the SIS, what you have here is a quadratic, no, or a third time correlation. Then you have to make something like this to close it. If it's linear, it's exact, right? But if not, which is the usual case, then you have to make an approximation to close the system. Also, when most of the times what we do is also we neglect a structural correlation, not only dynamical correlation, but also a structural correlation. For example, in the complementary approaches, we are assuming that the only important thing is the degree distribution. No, so basically, we fix the degree sequence. All the networks should be characterized by the degree sequence, which is also an approximation. This means that the approximations are valid when the networks are generated by the configuration model. Now we have the nodes and the degree sequence, and we match the different links at random. In this case, the adjacency matrix, no, the average of the adjacency matrix is a product of the degrees. No, so this is another approximation that we do most of the times. So, what are the limitations of these theoretical approaches that we study? As I said, normally we neglect dynamical correlations, and also we neglect structural correlations. But can we improve this? Can we improve the methods or generalize the methods to take into account also dynamical and structural correlations? And the answer is yes, sometimes we can do that. But in other cases, it's very complicated. No? I will show now that for dynamical correlations, we can do something. And for structural correlations, it depends on the network. For example, we have community structure, we have a network that is grouped in cohesive groups, is in communities. And these communities can be taken into account in the theoretical description. Then we can generalize the methods to take into account the communities. But for other networks, like, for example, spatial networks, where the nodes are embedded in space, this is very difficult, right, to approach these type of systems, and I will show you why. So first, can we take into account dynamical correlations? So these are fluctuations, etc. Yes, we can. For example, in these two papers, we developed the stochastic version of complemental approaches, where we take into account the full master equation, the full fluctuations and correlations of the system, and we can solve it. For example, this is for the noisy water model on different networks with average degree 4. This is the deterministic approach that is neglecting correlations. And these are numerical simulation in Erdos-Renyi and Barabasi-Albert networks. And this is the lattice case, 1D lattice and 2D lattice. So when we take into account the deterministic pair approximation, this is, by the way, this is the density of active links versus the noise intensity. When we take into account the deterministic approach, the approximation is accurate in a zone, but it fails for low noise. But when we improve it, when we make the stochastic version, we apply the stochastic version, we can recover the full analytically, we can recover the full results of the numerical simulation. So we can take into account dynamical correlations in an effective way, and we can solve it. So this limitation, we can do something. What about community structure? So when we have community structure, for example, when the network is obtained from the stochastic plot model, basically nodes are grouped in the network, where in groups that are the number of links is high inside the group but low between groups. So for example, this is the matrix of edge counts between groups, and it's a diagonal matrix, no, with small values outside of the diagonal. So this community structure is not taken into account in the theoretical description. So what can we do? We have to take into account the partition sequence, so which group each node belongs to in the theoretical description. So in these description variables, right? Here we are taking into account the state, the degree, and the number of infected neighbors. So we have to add here the compartment, the group which the node belongs to. So we need to add more variables to the system, and then we can do something. This, for example, this is an example that we study in this paper. For example, when we try to understand dynamics of polarization, this is a real network. This is political blocks network of the Liberal Democrat in the United States in 2004. These are the simulations. So we start from an initial state that is slightly polarized. So these nodes are in state. They are are in state 1 and half are in state 0. And we let time evolve, and the system polarizes more and more. So the ones that were in blue become more in the 0 state, and the ones that were slightly in the 1 become more to the 1. This is an example of a dynamics of the noisy model type. So can we do a theoretical approach to characterize these dynamics? Yes, we can. As I said, this is a vector field that we obtain from the compartmental approach in the heterogeneous mean field case, where we take into account the partition 1 or 2 in the description variable. So this is the density of nodes in state 1 and in partition 1. And this is the density of nodes in partition 2 and in state 1. And we get a set of coupled differential equations for the densities in each partition. And already with an heterogeneous mean field, we obtain results that are very accurate as compared to numerical simulation. So this is the vector field from the theory, these equations. The fixed points are what we obtain from this system of equations. And the red lines are the simulation in the network. And we can see that the simulations follow pretty closely the vector field and end up in the fixed points. So if you look here, this fixed point is consensus in blue, and this is consensus in red. And this zone is the polarization zone, where the system goes to a polarized state. Okay, so we can take into account community structure. For example, when we study polarization, it is important to take into account community structure, and we can generalize the theoretical methods for this case. But now, what happens when we have other types of networks that are not generated by the configuration model? They are also not community structure, or they are, but there are so many communities that it's impractical to take it into account. For example, when we have a random geometrical graph, that is one of the simplest models of spatial networks. What we do is we have an embedding space. For example, in this case is the 2D space. We position nodes at random in space, and then we put a link with a probability P for all the nodes that are, for example, in a sphere of radius R. So for example, we take this node, we make a sphere here, and all the nodes that are inside the sphere, we put a link with probability P. Okay, so this is called large wall networks, right? Because if we want to go from here to here, we have to make a long journey in between, right? What you position them at random, and then and then you put a link with this rule. Now, if the nodes are inside the distance between nodes is lower than some radius, you put a link with probability P. These networks are hard to study. No, there's little things that we can do, but one of the things is simple things that the average degree, or the average degree is n times p times the volume of the sphere, where Vd is the volume of the d-dimensional sphere, right? Because all the links here basically is proportional to the volume. In the Erdős-Renyi limit, the random graph limit would be the case in which the radius is infinity and the probability goes to 0, and k is fixed. So we have a model that with some parameters we can tune if it is more spatial or more Erdős-Renyi-like. Okay, and what can we do? I already tell you that all these methods that I explained before fail for this case. So they are not good enough to study the dynamics. So what can we do is to find some structural measures that tells us something about the dynamics. And one of these structural measures that we study is the path length distribution. So path length distribution is the number of nodes that are from distance L to one node, right? So we take a central node, and one will be the number of first neighbors, L2 will be the number of second neighbors, L equal to 3 will be the number of third neighbors, and so on. So we can think this as a dynamical process also. We start from a central node, this spreads to the first neighbors, then to the second one, and we want to know how this grows. In a d-dimensional lattice is easy, you can do it. It's just the average degree times a power law of the distance, so it's L to d minus 1. So it is a power law, this function, and for small world networks, it's an exponential function, because information spreads exponentially fast to the distance. This is the average degree, and this is the excess degree. Okay, we have for d-dimensional lattice, we have a power law. For a small world network, we have an exponential. But what happens for a random geometric graph? For a random geometric graph, it depends. We also find something similar to a d-dimensional lattice, but this exponent can be anything, can be it's a real number. So we call this effective dimension. This is an example of 500. So nodes, p equals 0.1, d equal 2, and average degree equal 4, and the effective dimension is something lower than 2. But this is just an approximation. And what we find is that this effective dimension depends on the embedding space dimension, on the average degree, and on p, but not on n. Okay, but this is just a qualitative description of the network. Does it work for dynamics? It does, but only in some cases. Now, for example, let's go to the very simple case that we explained before, the noisy water model, right? We make the same figure as I showed before. This is the average density of active links as a function of noise for random geometric graphs with average degree 4 and 5,000 nodes. This is the Erdős-Renyi case. This is the 2D, and this is the 1D. And this is the pair approximation in the deterministic version. And what we can see is that, okay, it makes sense, no? This effective dimension makes sense in the sense that for p equal 1, it is close to 1D. And as we decrease p, the curves begin to increase until you reach the 2D case. And then it also keeps increasing until you find the Erdős-Renyi. So by tuning p, if you remember, p small is Erdős-Renyi, p equal 1 is the spatial case. And by tuning p, we find different behaviors. So this idea of an effective dimension makes some sense, But for the SIS, if you try, it is more difficult, right? For the network-Renyi, this is the infected density as a function of the transmission rate. For the network-Renyi, as you increase system size, the bifurcation becomes, you find a critical point, no, the epidemic threshold, and the epidemic grows linearly, theoretically. No, this is following the heterogeneous mean field, for example. And as you increase system size, the curves converge to some value, to a theoretical value. If you try in random geometric graphs, you find strange things. No, first, well, you find something similar, but there is a very slow convergence in the thermodynamic limit. These curves converge very slowly. Also, there is a high variability of a network realization. So this is an average over networks, but 400 networks. But if you take two networks generated by the same model, the curves are completely different. And also, finite size scaling is not valid. So this is a very challenging problem, no? The SIS on large walls. So now let's move to the second part of the talk. Now I will talk about polarization that is related to the community structure that I explained before, the dynamics of polarization. And in this study, what we did is to analyze a data set, a Twitter network that was collected in 2019. It's a network of users, of Twitter users, Twitter accounts. The nodes are the Twitter accounts. And we make a distinction between parliamentarians, the politician accounts, that are 800, which are the parliamentarians in France. So this was in France. And users, which are the followers of the politicians. So the network is composed of politicians and followers. And the links are directed, and it's the follower-follower relation between the source and the target. So we have a network of politicians and followers. And we also know, of course, we know the parties of the MPs. We know the parties to which they belong to. These are the parties in a left-right scale. No, these are the most extreme right, and these are the center, and these are the left parties.
Is that qualitative or quantitative?
This is from a survey of politicians, of political scientists that they basically invent some scales, for example, this one, left, right, and they position in a survey, like position this party from 1 to 10 in a scale from left to right. And this is the position of the parties that they made on the survey. Okay. So what we do to analyze this graph, we take first the user MP graph. So the MPs and the followers of the MPs. Okay, we focus first on this graph. Why this graph? Because this graph tells the attitudes, the political attitudes of the users. No, users that are following left parties, we assume that they are left ideology. No, they have left attitudes, and people that follow right, they are from the right wing, right? So we analyze this network. There is the adjacency matrix. Now we have a table where we have the followers in the rows and the MPs in the columns. And if follower 1 follows MP1, we have 1 here, if not 0. No? And we construct this table of the MPs that follows each of one of the users. If we sum the columns, we have the in degrees of the MPs. And if we sum the rows, we have the out degrees of the followers. So how many MPs a follower has followed, and how many followers have an MP. No, this is the table. If we apply the configuration model, no, as before, we neglect structural correlation, then the adjacency matrix should be approximately the out degree times the in degree divided by the number of links. This is the configuration model. But as I said before, when we use the configuration model, we are neglecting correlations, community structure, and so on. So what we are interested is in the deviations of the configuration model. So deviation, or the residuals matrix, is the adjacency matrix minus the prediction of the configuration model rescaled by the degrees. Okay, so we focus on this network, on the deviation from the configuration model. We apply the singular value decomposition of the residuals. So this is a diagonal matrix. This is a change of basis, this matrix, and we get the coordinates of the nodes in a space that we call the latent space. Okay, these coordinates are simply the values of this diagonalized space, which is the latent space. Okay, and we get positions of each one of the users in a dimensional space. Okay, and also not all the dimensions of the space are important. No, we have a way to know which one of these dimensions is the most important. That is the inertia. The inertia is just the diagonal value of the matrix to the square divided by the total. And this is the inertia for the different dimensions. So we have a space with a lot of dimensions, but only the ones that have higher inertia. No, the inertia is how much of the residuals matrix you cover with the dimensions. So we focus on these 4 dimensions. Okay, so basically what we have done is we have the network of the followers and MPs. We make this correspondence analysis, this residual matrix. We make the singular value decomposition, and we get some positions of the nodes in a dimensional space. Now, the curious thing is that if you compare the positions of the nodes in this latent dimension, which in principle is, it doesn't have any political meaning. No, it's just a mathematical method where to embed the nodes in some space. If we map the positions in the latent space with the positions in a reference frame, which is this chess surveys that I explained before, this chess surveys are political scientists that position parties in a space, and this space has some political meanings. Dimensions have political meanings. So if we plot the positions of the parties in the trade protectionist space and the dimension, or the left-right dimension, we find correlations between the first latent dimensions and the chess surveys dimensions. So what does this mean? This means that this latent space has the positions have or reflect somehow the ideologies of the users or the attitudes of the users. And this is, for example, this is the results. This is the positions of the politicians in this space, no, in the reference space, where these are the dimensions. Okay, the names are not so important, but they reflect somehow attitudes towards left, right, towards EU, the nationalists or elites. And as you can see, this is the positions of the politicians in space, and the colors are the parties, the different parties. And what you can observe is that it works pretty well, in the sense that you can see that, for example, the socialists are in the left zone, the right parties are in the right, this is the center, and these are the communists. So this space somehow reflects, you know, the attitudes, the political attitudes of the MPs, of the politicians. Now, with this method, we obtain the positions of the politicians, but we also obtain the position of the users. And in this plot, what we are comparing is the politicians, which are orange, and the positions of the users. Users are in blue and politicians are in orange, and the color is the popularity of the politicians. So the ones that are darker are more popular. And this is the histograms of the positions. And what we can see from the plot is that the politicians have less extreme attitudes than regular user. Not all the positions of the politicians are inside the blue zone, which means that the politicians have less extreme attitudes. And also what we can see is that the users align with the most popular politicians. Now the positions, if you see here, all these are the most popular politicians because they have more number of followers, and the users are concentrated in the zone of the most popular politicians. Now, what can we do also? We can take the network. Now we focus on the follower network of the politicians, for which politician follows which one, this network, and we can run the, community detection algorithms. So we can partition the network in groups, and we find the best partition has 5 groups. These are the edge counts, the number of edges that go from one group to the other. So these are the 5 groups that we found. These are the names that we call them because of these are the party composition. So the left group aggregates all left parties, the center parties, and 2 rights. One is the nationalist and other one is the liberal. So if from this partition, this is the community detection algorithm run on top of this network, and we plot the attitudes of the politicians in this where the colors are the communities, and what you can see is that the communities that with the same color are clustered in the dimensional space. So this also makes sense. That the communities which are left are clustered in the left zone, and communities that are right are clustered in the right zone, and also for the center. So what can we tell from this is that the structurally cohesive groups, so groups that are more connected between them, also share political attitudes, which makes sense, right? So this is the politician network. Now we are going to the user. So which of the followers follow other followers? Again, we make a partition of the network into 4 optimal groups. These are the distribution in the left-right dimension. We have this is the left community, these are the center, and this is we can call the far right. So these are the distribution of aptitudes of each one of the communities. And what is interesting now is that we plot here the distance to the center. So we split the opinion space in bins, in small regions, and we plot the fraction of links that go to another community. So this is a measure of segregation. How many of your followers are not from the group? If this is high, it means that so for example here 0.6 will be that 60% of the links go to another community. And if it is 0, is that all the links are in the same community. And what you can see is that this is the extremist or the left and right communities. You have a decreasing tendency. What does this mean? That the more extreme your opinion is, the more segregated it is in the network. So the more you go to the extreme, the less you are connected to the other groups. Also for the right community, the more extreme you are in the right scale, the less number of links go to another community. So the more segregated you are. While for the more center communities, you find a flat pattern. So this means that the center community link to other groups more or less homogeneous, in a homogeneous way. So what can we tell from this is that the groups with extreme political attitudes are more segregated in the network, which also makes sense. So as a final remarks, first I reviewed all the theoretical methods that we have for dynamics on networks. These are individual and complemental approaches. We have shown that these approaches have limitations, and in some cases we can improve the approaches to take into account other structural factors. So we can improve these theoretical approaches in some cases, And then we have analyzed a network of Twitter related to politics in France using embedding and community detection methods. And we have found four properties of the network. One is that structurally cohesive groups share political attitudes. So the groups have common political opinions. We have also shown that professional politicians have less extreme attitudes than regular users. We have shown also that the opinions of the users align with those of the most popular MPs. And finally, that groups with extreme political attitudes are more segregated. That the more extreme your opinion is, the more segregated you are in the network. And this is all.